What if the bright comet barreling into our solar system isn't a comet at all, but a powered craft quietly testing how we respond? On July 1, 2025, survey telescopes flagged an interstellar object now labeled 3I/ATLAS, moving faster than 200,000 kilometers per hour and slicing through our planetary neighborhood on a path that lines up almost uncannily with the orbits of multiple worlds. Most scientists say it looks natural. A few, including Harvard astrophysicist Avi Loeb, argue that parts of the data hint at something far stranger: light that might be self-generated, not just reflected from the sun. If that's true, 3I/ATLAS could be far smaller than it appears, far more capable than we imagine, and its timing may be no accident. Here's what we actually know. 3I/ATLAS was discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, using a new Chilean telescope tuned to catch fast movers. The moment its orbit was computed, the numbers shouted, "Interstellar." Its eccentricity sits well above 1, which means it isn't bound to the Sun. Like Oumuamua and 2I/Borisov before it, this thing is a visitor from another star system, here for a brief pass and then gone. But two early clues set it apart. It's traveling retrograde, the opposite direction most planets and asteroids go, and its orbital plane is tilted by only a handful of degrees relative to the ecliptic, the thin disk where our planets ride. That combination, retrograde motion yet so closely aligned to our planetary plane, is rare for a random rock wandering in from deep space. Now to the riddle that lit the fuse. Hubble images reveal a surprisingly steep brightness profile. The glow drops off from the center faster than we see in typical comets. If you assume ordinary reflection, sunlight bouncing off dust and ice, you end up with an object tens of kilometers across. The rough number lands near 20 kilometers. That would make 3I/ATLAS a giant compared to earlier interstellar visitors. But there's a catch. The odds of randomly catching a 20-kilometer interstellar body are painfully low. You could wait thousands of years and never see one, which is why a provocative alternative has serious people leaning forward. What if at least some of that light isn't reflected at all? What if it's generated by the object itself? Flip that switch and everything changes. If 3I/ATLAS is self-luminous, the true body could be hundreds of meters across, not tens of kilometers. Suddenly, the statistics make more sense. You're not invoking a once-in-10 millennia monster to explain the glow. You're allowing for a much smaller, rarer than normal, but not impossible visitor that happens to shine. Spectra complicate the story in the best possible way. Observations from major facilities report strong signatures of water ice mixed with carbon-rich dust and silicates, the exact cocktail you expect in a comet forged in a cold nursery around a distant star. Some readings even hint the water could be unusually pristine, lacking the heavy isotope fingerprints we often see in our local long-period comets. That's consistent with an object born under different stellar chemistry. So case closed, right? Not quite. The tech camp counters that an interstellar craft could accrete a jacket of dust and ice over eons, wearing a natural disguise while a power source inside does the real work. If you've traveled for millions of years through the interstellar medium, you come home wearing that road dust, whether you're a comet or a probe. Trajectory is where the hairs on the back of the neck start to stand up. 3I/ATLAS isn't just passing through. It's set to thread the needle near multiple planets. It will skim past Mars at roughly 29 million kilometers around October 3rd, then swing to Perihelion, its closest solar approach, near 1.35 astronomical units on October 29th, and later come within about 33 million kilometers of Jupiter. Stack those alignments, and the probabilities for a truly random interstellar object drop to eyebrow-raising levels. Add this twist. During perihelion, Earth is on the opposite side of the Sun. Our planet won't have a clean line of sight, while 3IATLAS is at its most interesting. If you wanted to attempt a high-thrust maneuver near the Sun, a reverse Oberth move to shed speed, and maybe stay in the solar system, you could hardly pick a better time to avoid our telescopes. Before we jump to conclusions, we have to confront the mainstream view. Most planetary scientists still believe 3I/ATLAS is a natural interstellar comet, waking up as it warms. Dust production rates inferred so far, on the order of a handful to a few dozen kilograms per second, are perfectly reasonable for a small, icy body beginning to vent. Ejection speeds from tens up to a couple thousand meters per second fit what solar heating can do when volatile ices start to sublimate and push grains away. And the absence, so far, of strong gas lines like CN or C2 isn't alarming at 4 astronomical units. Many comets stay whisper quiet until they move closer to the Sun, then flicker into obvious activity. Under that lens, the steep brightness profile might be explained by unusual grain sizes, jet geometry, or the angle we're looking from, not by a built-in light. The self-illumination idea also faces a brutal energy bill. To match the observed glow with intrinsic light, back-of-the-envelope math lands near 10 gigawatts, several large power plants worth of output. You can try to get there with natural radioactivity or other heat sources, but keeping that kind of power going for interstellar timescales strains credulity. A technological emitter, advanced reactors, engineered radiators, or some directed illumination solves the power question on paper, but it replaces one improbability with another even bigger one: the presence of alien technology operating in our backyard. Extraordinary claims ask for extraordinary, testable evidence. That's the beauty of the moment we're in. Over the next few weeks and months, data can break the tie. As 3I/ATLAS closes in, watch for the thermal and spectral fingerprints of a normal comet to blossom. If the brightness tracks with solar heating, if standard volatiles flare at predictable distances, and if any non-gravitational accelerations match the rocket effect of outgassing, the natural case strengthens. If the light behaves like a stubborn outlier, too bright, too steady, too decoupled from heat, then the conversation gets interesting fast. There's also a narrow but electrifying opportunity as it brushes past Mars. Teams have discussed using instruments like the HiRISE camera aboard the Mars Reconnaissance Orbiter to snap high-resolution frames as 3I/ATLAS sweeps by. Even a handful of resolved pixels could tell us whether we're looking at a dusty coma around a small nucleus or a more structured source of emission. Down here, Hubble and the James Webb Space Telescope will probe temperature, grain sizes, and brightness laws in tandem. Does a straightforward reflective model fit? Or do we keep finding edges where it doesn't? Meanwhile, the dynamics folks will keep their eyes glued to the trajectory. Comets often show subtle course changes as jets turn on and off, but those nudges are tied to measurable venting. If 3IATLAS starts to drift in ways that don't line up with the gas we see, or if it executes a timing-perfect tweak near perihelion while Earth can't watch, the engineered hypothesis gets louder. After the Sun, the Jupiter leg offers another stress test. Graze a giant planet, and we can sometimes catch small changes that expose what's pushing the object besides gravity. To frame all this, it helps to remember our last two interstellar surprises. Oumuamua, our first, behaved like a thin pancake or shard, accelerated slightly without a visible coma, and left us with more questions than answers. 2I/Borisov looked like a textbook comet, with a broad, dusty tail and familiar gases glowing in sunlight. 3I/ATLAS could be the tiebreaker. If it settles into normal comet behavior as it warms, we'll chalk Oumuamua up as a weird end member in a broad population. If it keeps playing against type, we may be staring at a category we haven't defined yet. All of this unfolds just as the Vera C. Rubin Observatory spins up to full science operations. Rubin will catch dozens of interstellar intruders per year, giving us the statistics we've never had. With a real sample size, we'll finally learn how often visitors look like Borisov, how often they look like Oumuamua, and how often they look like whatever 3I/ATLAS turns out to be. That matters because one object can fool you. 10 start to tell a story. 100 write the rules. Let's return to the fear in that headline. Why scientists fear what 3I/ATLAS might be. It isn't fear of monsters, it's fear of being wrong in the best possible way. If this object is natural, yet mimics self-illumination because of exotic dust physics, unfamiliar ice chemistry, or a geometry we rarely see, it means our comet models are missing chapters. That's thrilling and humbling. We'll rewrite the playbook, update the brightness laws, and move on smarter. If, against the grain, the evidence keeps resisting a natural explanation, if the light, heat, and motion refuse to line up with solar physics, we'll be standing at the threshold of the most consequential discovery in human history. Not just life elsewhere, but technology designed and operated by a non-human intelligence now passing through our system. So how do you, watching from home, read the next wave of headlines like a pro? First, look for whether the brightness can be explained with reasonable albedo and dust properties. If astronomers can fit a standard reflective model without resorting to absurd parameters, that's a point for Comet. Second, watch the thermal data. Temperatures that rise and fall exactly as sunlight dictates argue for a passive reflective body. Persistent excess heat at distances where it shouldn't be there keeps the self-lit question on the table. Third, pay attention to gas detections. As it nears 1.5 astronomical units and closer, standard molecules should pop. If they don't, that's odd. If they do their amounts match the push we see in the trajectory? Fourth, keep an eye on timing. Any course correction conveniently hidden behind the sun will spark debate. And finally, hope for images. Even crude structure beats 1,000 speculations. There's a human element to this too. Scientists are not a monolith. Some will push the conservative explanation until the last anomaly falls into place. Others will probe every crack for signs of engineered behavior. That tension is healthy. It's how we keep from fooling ourselves in either direction. The key is to let the object lead. 3I/ATLAS will tell us what it is if we ask the right questions fast enough. The calendar matters. Early October brings the Mars Pass, our best shot at an off-Earth camera looking in. Late October is the perihelion swing at 1.35 astronomical units, when heat, gas, and dust should spike if this is a standard comet. December may bring an Earth-side geometry change and a modest flyby, with fresh chances to measure any non-gravitational shoves. Each checkpoint is a filter. Pass the comet tests, and the natural picture clicks into focus. Fail them, and we'll be forced to consider the extraordinary. Whichever way it goes, the stakes are enormous. If 3IATLAS is natural but weird, our models get better, and the next anomaly won't blindside us. If it's artificial, even in some limited sense, say, a relic with active power systems rather than a fully steerable craft, we'll have proof that intelligence has operated beyond our sky and left fingerprints we can detect. Either outcome is a win for curiosity. Either outcome enlarges what it means to do science in public, in real time, at the edge of the unknown. I'll leave you with this. Space doesn't owe us explanations. It gives us puzzles and a ticking clock, and asks whether we can keep up. Right now, 3IATLAS is the puzzle of the decade. It's bright enough to tempt us, close enough to study, and odd enough to challenge our priors. In a matter of weeks, we'll have data no one has ever had on a third interstellar visitor weaving through our system. If the light is only sunlight, we learn. If the light has a source, we learn something bigger. Keep your eyes on the Mars Pass, watch the perihelion numbers, and stay curious. The universe is about to answer a question we didn't even know how to ask 10 years ago. And it's racing toward that answer right now.